Hello, my name is Matthew Marquardt and welcome to the Unwrapping in 3D Studio Max video tutorial series. In this first video titled Fundamental Unwrapping Concepts, we're going to learn the basic core ideas and terminology behind unwrapping. This particular information is mostly program independent, meaning if you want to jump straight into 3D Studio Max and just learn its tools, I'd advise you to skip to the second video in the series and so on. Let's begin with a definition of unwrapping. Unwrapping is the process of plotting out in 2D where and how a texture will be displayed on a 3D model. In other words, think of it as creating a 2D roadmap of how your texture will navigate the surface of your 3D geometry. This image explains the idea perfectly. On the far left, we see a cube with a texture on it. In the middle, we see the same texture beginning to break off the model, while the last cube shows the texture now completely flattened out as if we just unwrapped a present. This is the basic concept of what we are doing when we unwrap. We are finding a way to turn a 3D object into a 2D plane so we can transform that into an image in which to paint a texture onto. Before technology progressed to where it is now, 3D artists would literally unwrap a model by separating and flattening every polygon of the geometry. In fact, this is where the term unwrapping came from. Fortunately for you, however, the technology has vastly improved with tools and programs that significantly speed up this process. While looking at an unwrap for the first time, it may feel overwhelming and overly complex. In reality, unwrapping is actually quite easy. However, due to its concepts being so foreign for a beginner, it often requires time and repetition to gain a good grasp on the inner workings of the process. So if you're finding yourself having a hard time understanding it, it is literally just a matter of getting in more practice and experience before things will start making more sense to you. As such, be patient. Now that we know the general concepts of unwrapping, let's take a closer look at the workspace we'll be unwrapping within. While this is the UI of 3D Studio Max's workspace, the concepts and layout are the same no matter what program you'll use to unwrap. As explained by this overlay, what we see here is the translation of UV space. The U space spans on the horizontal axis, while the V space spans on the vertical axis. The box that is defined in the middle of our workspace here represents the texture or image the UVs will be mapped to. The extents of this box go from 0 to 1 in both directions as seen by these coordinates. Anything that falls within this space only repeats once. However, any UVs that pass the extents of this box will repeat the texture infinitely in any direction. Similar to world wrapping in video games where you leave the boundaries on one side of the screen and you come out on the other. When your UVs spill past the box's boundaries, the texture that is now displayed in the UVs will be mapped to the other side of the repeating texture. To better visualize all of this and to help define a few more unwrapping related terms, let's jump into Max for a moment. This here is a relatively simple model that I created for the Star Wars Clone Wars Adventures game a long time ago. The ship was only meant to be seen from a distance, therefore it's low poly with the details coming mostly from the texture. This example, however, helps us see what a final unwrap could potentially look like and how it displays on the geometry. Each one of these sections in the unwrap is known as a UV island. The outer edges of the UV island, as defined by the green line seen both on the model and in the UV editor, are known as seams. If I was to grab, say, this island here and move it, you can see how what is being displayed on this section of the geometry changes, but only within the area defined by the seams. If I want to change another area, I'll have to find and manipulate the UV island on that section of the model. Going back to the point I made before we jumped into Max, leaving the boundaries of the box repeats the texture as you can see here. Notice when the island is partly in the box and partly out of the box, the section that is outside begins to display what is on the other side of the texture. When I scale the UVs up, this allows me to repeat the texture as many times as I want on the geometry, as you can see here. Doing so intentionally is how you set up the UVs for what is known as tiling textures, but I'll cover more on that in a moment. Of course, on the other end of the spectrum is what I did for this model. The process of fitting all the UVs into this box is known as packing. And finally, the space left in between the UV islands is known as padding. When packing the UVs, the goal is to use as much texture space as possible as evidenced by this example. Any unused space, as defined by any space not being covered by the UVs, will simply be wasted. While this might not sound like a big deal, the truth is when running a game, all the textures in the scene are fully loaded into memory, regardless of how much is actually being displayed on the geometry. Part of the artist's job when it comes to optimization is learning how to properly pack UVs and knowing what is an appropriate amount of padding between the UV islands to best avoid texture bleeding. The core process of unwrapping can be summed up by how you personally choose where your scenes will go, which of course defines your UV islands, how you manage distortion, more on that later, and how you pack and pad those UVs. A texture sheet is basically any texture that isn't meant to repeat. Like with the example of my Star Wars ship, you can see my original unwrap, the texture I painted using the unwrap, and how they look together to best see how the unwrap influenced the texture painting. Here's another example of a finished texture sheet and how it looks on the geometry. So when you're doing a texture sheet, you'll first unwrap your model, then you can export out your UVs into an image like I have here. And finally, you'll import said image into a program like Photoshop to paint the texture. More advanced programs like Substance Painter allow you to import the entire unwrapped geometry into the program so you can paint on it directly. But with either approach, you need to create and export a final texture image to use with your game engine of choice. A tiling or seamless texture, on the other hand, doesn't need UVs first. A tiling texture by definition requires repetition on the geometry. As such, unlike a texture sheet whose goal is to stay inside the UV box, the UVs for tiling textures actually expand out past the initial UV box as much as needed. The more the texture tiles, the larger the UVs are. For a lesson on creating tiling textures in Photoshop, click the link in the top right corner of the video. Now in this image you can see the base texture only has 4 dark tiles. However, when we scale the UVs out 9 times the size of the box, the image repeats just as many times in the geometry. So remember, when you're doing a texture sheet, you'll keep your UVs inside the box, and when you're doing a tiling texture, you scale it outside the box as many times as you need it to repeat. Texture sheets are designed for specific geometry, think basic assets, vehicles, or characters, while tiling textures span generically over larger spaces, think terrain or long walls and floors. Now let's talk about the important concept of texel density. Texel density is the relative texture resolution being projected onto a 3D surface. This means the higher the density or the more texels in a given area, the clearer and sharper the textures will appear, while lower densities lead to muddier, blurrier, and more pixelated textures. Obviously, in a perfect world, we'd always want our textures to look clear and sharp, so higher texel densities for the win. But when it comes to current technology and real-time rendering, it's just not possible or practical to always keep our texel density extremely high. To better understand texel density, let's look through a few visual examples of it in action. In this image, we see 3 boxes. Each one is progressing in size by a power of 2. All 3 boxes are using the same exact texture at a resolution of 512 by 512. This means the small box has a much greater texel density than the last. As a result, the 512 horizontal pixels within the texture being displayed on the large cube must stretch 4 times the visual space of the first cube. This makes the texture on the final cube look more blurry and pixelated when compared to the first. To better see this, let's match the texel density of the first cube onto the last. Look closely at the zoomed up area as I change the images back and forth. This is what the fixed texel density now looks like. This is what the uneven or lower texel density looks like again. And back to the higher one more time. The first factor that can control texel density is resolution. The resolution of the texture must match the relative size of the geometry it is on. The reason the texel density is now fixed on this image is because the texture resolution now matches the size of each cube. Instead of being the exact same resolution, the textures now increase at a power of 2, matching the scaling of each cube's size. The first texture is still 512 by 512, but the next texture is now 1024 by 1024, and the last has been changed to 2048 by 2048 pixels. Now the other factor that controls texel density is UV scaling. In this image, we see 4 cubes increasing in size from 100 to 400%. These boxes also have the same image with the same resolution on 4 of them. However, this time, instead of swapping out the textures for versions with higher resolutions, we're going to change the size of the UV islands in the unwrap. So while the texture is left alone, simply shrinking the UVs of each of the smaller cubes can also fix texel density issues. This is how the UVs map to the first cube, the 2x cube, the 3x cube, and finally the 4x cube. This also means that when you use a tiling texture, you need to pay attention to how often it is repeating. The image on the left has the texture only displaying once in the UVs, making the texture look muddy and the stone tiles too large. The image on the right is tiling 8 times more, making the texture look too sharp compared to the other objects around it and making the stone tiles seem too small. The correct amount of tiling would be somewhere in the middle of these 2 examples. So the 2 factors that control texel density are texture resolution and UV scaling. That leads us to our next topic, texel density consistency. As a rule of thumb, you typically want to aim for 1-to-1 texel density throughout both the model itself as well as model-to-model consistency throughout the entire scene. Realistically though, most subtle density differences won't be very noticeable. It's only when the density difference is large enough between either adjacent polys or objects in the scene that it can potentially ruin visual fidelity. And we see that quite clearly in this image. Notice a nice texel density on the barrels and the buckets, and even on the texture on the wall. But we're starting to see a little drop off in the density on the wooden beams and supports, and we have some horrendously low texel density on the floor where we could literally count the pixels. This image, created for another, more in-depth texel density tutorial by the artist listed here, shows off what poor texel density consistency looks like on the left, and on the right, we see what perfect consistency looks like. The variation between the left and the right scene is often the most crucial difference between the work of an amateur versus the work of a professional. Be sure to spot it out in your own work. So now let's talk a little about texture scale. Take a look at this brick, for example. Are the bricks small or large? Well, the answer is completely relative. When these other brick textures are brought in, we can now make a better assessment. Keep in mind that all three of these textures are at the same resolution. This means that the photos these textures were made from were taken at different distances from the wall. Simply slapping them onto an object and calling it a day isn't enough. It's usually smart to have objects in your scene that represent a baseline scale. I'm using the 6-foot man I found in TurboSquid. To download him for use in your work, check the link in the description below. I've also placed a typical to scale brick in the scene to see what these textures look like in comparison. When you have something to compare scale with in your scene, you prevent the issue that occurs when you are merging multiple scenes together, or when importing your work into a game engine for the first time, only to discover in both situations your geometry is either insanely massive or extremely microscopic. Keep in mind that these walls are at the same size, the UVs are the same scale, and the textures are at the same resolution. The difference is simply the scale the texture image was taken at. So while seeking good texel density is important, don't forget to use a texture image that is at the right scale. No one cares your texel density is perfect when the bricks look either the size of stairs or toothpicks. You could scale the UVs to tile less or more depending on the texture, but now your texel density is off again. So it's also important to pay attention to the original scale your texture image was taken from. This isn't to say there aren't occasions when texel density is intentionally varied in the unwrap, but the key word here is intentional. There are several situations in which this could be done. In this quick scene created in Unity, you can see a tiling grass texture on the ground and a tiling rock texture on the mountain. The grass is repeating quite often and looks pretty good when staring down directly upon it. While the rock texture also looks good from a distance, look how the texel density appears to change as you approach it. It's actually pretty low, especially when you compare it to the grass right next to it. In situations when it's rare for the player to see an object up close, or basically any geometry that might only be observed from a distance, the texture might be intentionally tiled low to keep the detail from repeating too much. When the rock texture on the mountain tiles at the same rate as the grass, the mountain doesn't look as good from the intended distance the player will see it at. That's the issue with tiling textures that have high contrast detail. When they repeat often, you can spot the repetition and it looks pretty bad. So the detail on this low density version looks more appropriate in this situation. On the other hand, the high repeating, high texel density grass looks fine as a result of the low contrast details and the mip mapping Unity automatically applies to the textures in the distance. An example of mip mapping can be seen with this image. The image on the top left has no mip mapping. We can see some texture banding and distortion as the texture moves away from the camera. The top right image shows the same crate, but this time with mip maps on, resulting in a softer, more natural fade in detail. The image on the bottom is what the texture looks like with all the included mip map resolutions. Mip maps are basically varying degrees of resolution on the same texture that are loaded and blended with each other at specific distances from the camera. This, of course, is meant to emulate the way we see when we look off into the distance in real life, with the detail slowly degrading the further and further we are from an object. In this image, we see more of an extreme example of mip mapping in action when the texture gets so far away from the camera it basically looks like a solid color in the distance. Another major reason for intentional texel density variation is when it comes to textures that require high levels of detail. Intelligent and experienced artists know when and where texel density can be varied while still maintaining the appearance of cohesion that a consistent texel density would provide. Characters are a perfect example of when this ideology can be applied. While the art on the textured character on the right looks great, it's obvious when looking at the checker mat version of the character that the texel densities are extremely varied. In fact, you can even see the UVs in the arms, undershirt, and shoes are being stretched. All of this was carefully planned for both detail and optimizational purposes. While normally all stretching and distortion in UV should be removed, more on this later, in the case of solid colors and simple gradients, you can get away with it as evidenced by this image. This lets the artist use more texture space on things that require higher levels of detail. Also notice that the highest densities are where the most detail is needed: face, necklace, and accessories. And the low and mid-level areas have less detail in the texture. This was done both in how the character was unwrapped and through varying texture sizes, as shown by the final texture seen here. The face, hair, and belts literally take up 5/8 of the entire texture space, even though volume-wise they're only about 1/10 of the entire character's mass. The density is therefore highest in these areas, allowing for clear and precise details where they are needed the most. You may have also observed that some parts of the character are only half painted. The face, eye, undershirt, pants, and necklace chain are some of these elements. This was done by intentionally overlapping UVs onto the same area of the texture. Overlapping UVs are a quick and resourceful way to texture, as it allows you to paint once but have multiple areas of the model covered simultaneously while also saving on texture space. This method works in many different situations, especially when parts of the geometry, like in the case of this character, are symmetrical. However, understand that overlapping UVs aren't allowed with some modern texturing techniques. Certain types of textures such as normal maps, ambient occlusion, and lighter shadow maps should never use overlapping UVs. But as far as textures that use only simple diffuse or color maps are concerned, it's obviously encouraged. In conclusion, while displaying wide variables in texel density, the artist, through careful planning and skillful application, was still able to create a very cohesive and optimized character design. The last major concept I wanted to touch on for this video is UV distortion and methods towards spotting and managing it. Over the course of this video, you have seen several images use checker textures on their unwraps. While it might be obvious why at this point, I still want to make sure everyone is on the same page. So why add a checker texture in the first place? By adding a material that has easily recognizable shapes, such as the perfect squares on this checker texture, determining the quality of your unwrap becomes much easier. This image is pretty clear. When a checker texture is added to an object like these cubes here, you can quickly determine the state of your unwrap with even a quick glance. Remember, we know the checker texture is made up of perfect squares, so when your unwrap is done correctly, the texture will display as you'd expect it to. However, when it looks wrong, you can spot out these issues such as the stretching we see on this cube, or even worse, skewing as seen on the final example. Recognizing distortion isn't always as easy as it appears in these examples. As a beginner, this tends to be one of the hardest skills to acquire. Sometimes you have to look closely. The cube on the left has perfect UVs, however the cube on the right only has 15% stretching. Looking at them side by side, it's hard to even notice the distortion. When I replace the perfect UVs with the stretched UVs, and then back again, it's more obvious. One more time. Now to be fair, distortion this minor might actually be hard for even the player to notice. In the end, all that matters is what the player sees from their perspective. But I'll cover more on that in a moment. Either way, when you're first learning how to unwrap, it's good practice to look closely at your model for all kinds of distortion, no matter how minor. But really, what's the big deal with distortion anyway? Why do we even want to avoid it? Well, let's say here's a texture we want to add to our model. It's an image of a nice circular button. Let's see what replacing the checker texture on our cubes would look like with this new image. Notice how the distortion affects the way our texture is displaying. Everything looks as intended on the first cube, but our perfect circle on the second cube now looks like an oval due to the stretching. And the skewing on the last cube makes the button look pretty ridiculous. So as you can see, leaving distortion on our UVs will translate to unpredictable and unwanted results in the final texture. But these kinds of distortion aren't the only issues we might run into. Let's go back to some new checkered cubes. The first cube has perfect UVs. The next two cubes, however, have some issues. Can you spot them? It's kind of a trick question. There is distortion, but with just checkers on the cubes, it's impossible to see it. Even though checkers are the default standard image used to spot distortion and unwrap, they aren't always perfect for every situation. Let's observe what happens when we now add the button texture to these new cubes. Now it might be more obvious where the issues are. As mentioned already, the first cube has perfect UVs. We can now see that the UVs on the second cube, however, are actually rotated 180 degrees. The UVs on the last cube are mirrored. So when we have a texture that is meant to have text on it, or any other recognizable object that requires a specific orientation to it, we need to also look out for rotating and mirroring. The perfect squares on a checkered texture look the same when rotated or mirrored. This is why some artists use an image such as this one, with text and more colors to best locate all the distortion issues, as clearly evident when applied to these same cubes. Some prefer the less busy look of checkers to start their unwrap to catch the major distortion. Then they switch to the more complex material for the last tweaks. Of course, there's also plenty of situations where rotation and mirroring doesn't matter in the unwrap, so there's no right answer. It's up to you, the artist, or the situation as to when you want to use each kind of texture. The truth is, however, it's fairly impractical to create an unwrap with literally zero distortion. Outside of breaking every single polygon into its own UV island, you'll have to work through some minor distortion, as the geometry you'll be creating will obviously be more complex than simple cubes. Your job as an artist is to not only be quick and effective with your work, but as far as distortion and UVing is concerned, what the player can see or notice in-game is all that really matters. The more complex your geometry, the more you'll have to manage distortion. Going back to the squall character from the previous video, we can see a few areas of bad stretching. The texturing didn't call for anything other than a slight gradient, so in the end, the artist was able to get away with it. Though as I mentioned previously, this was intentional. So once again, the most important question to ask is, what will the player see? If the distortion is distracting or obvious, take it out. If the distortion can be hidden or isn't even noticeable from the player's perspective, then you're safe to leave it in. The proper management of UV distortion during the unwrapping process is a skill that can only be acquired through time and practice. For now, focus on the tools and the basic process, and the rest will come to you later.